And
Miss Torella, I
Yeah.
hope I'm not interrupting, but did you possibly get my email by any chance?
who is asking?
Alyssa Komchinsky.
When did you send it?
Last night.
Yes, I did.
Okay, so am
Yeah.
I good to go by like 10 o'clock?
Yeah.
Or like 10:20? Thank you.
Yeah.
Sorry.
Yeah, just get what you miss. Okay.
Thank you so much.
You're welcome. I had gotten another email from somebody else this morning, and sadly, I don't recognize you guys by voice, so that's why I hesitated.
Oh,
I'm sorry.
it's okay.
Yeah. All right. This is where I want to start today is April 20th. We're going to be looking at angles, radians, and hopefully we'll get into a little bit of discussion about right triangles. Homework 8.1, that's the homework on systems. That's due by the end of the day today. Homework 5.1 right now is due by the end of the day on Thursday. I don't think it should be a major challenge for anybody. It's based on what we're doing today, but I think it's pretty straightforward. The next two homeworks will be due a week from today. We should be finishing up that material on Thursday. Problem set 4 will be due a week from Thursday. Test 4 will be problem set 4, I apologize, will be due the 29th, a week from Thursday. Test 4 will be due by the end of the day, Saturday, May 1st. Problem set final will be due by the end of the day, May 5th. The final will be due by the end of the day, May 6th. The last day that you can do any regular homework, not problem sets, not quizzes or tests, but homework in my lab will be Sunday, May 2nd. Again, I've gotten emails from different people at different points in time. It's past due. You can, if it says past due, you can still work on it. I don't have to, the only time I have to wave a magic wand to reopen it is if it's a test or a quiz. And technically in the syllabus, it said that tests and quizzes are due when they're due. If there's extenuating circumstances, reach out to me. But the homework you can work on at any point in time, which is why over the weekend, I think I heard from a couple of people, I tried to make sure that everything in Blackboard was current. So all of the quizzes got taken from the MyLabs gradebook to the Blackboard gradebook. All of the tests are in Blackboard. Again, the test grade that counts in Blackboard is the grade that was given to the work that you submitted. If you didn't submit work, that's problematic. But if you work on a back homework, there will be a late penalty depending on how late the homework is. It might be a severe late penalty, but honestly, in terms of an average, anything is better than a 0. The reason the homework is due by Sunday the 2nd is because then I go through it with a fine tooth comb. I look at everybody's homework and I look at any late assignments. Any late assignments, I will make sure, no matter what my lab says, I will make sure you get at least half credit for the work that you do on any late assignments. All right, now this is a slight change from the syllabus. The more I think about it, the less significant of a change it is, but everybody must take the problem set final. That'll be your last quiz grade. In the grade book, I will drop the lowest quiz grade. In the grade book, I will, in the MyLabs grade book, I will probably drop the lowest 2 or 3 homework grades. Now, in the syllabus, it says that there are 4 tests final. Final counts twice, giving me 6 grades, and I keep the 5 highest. The change that I'm thinking of making is I'm only going to count the final once. I'm only going to count the final once, and I'm going to keep the 4 highest. So if the final only counts once, and I'm going to take the 4 highest, what that means is if you're happy with your average after exam 4, there's no need for you to take the final. That would be the drop grade. So that makes the final optional. However, if you missed a test and got a 0 on it, you did poorly on a test, you're not happy with your average, then if you take the final, your lowest test grade will be dropped. So slight change from the syllabus. The more I think about it, the only real significant change is that the final is only counting once, not twice. So the final exam is optional. If you take it, the lowest test grade will be dropped. If you don't take it, none of your test grades will be dropped. It would be equivalent to the final exam being the grade that's dropped. Does anybody have questions about any of this? One last thing, looking at my calendar, give me a second because I have to pull my calendar up. The final exam will be due by the end of the day on the 6th. I will not hold class on the 6th. I will be in front of my computer with Zoom on, but it's not going to be a mandatory class. I will just be here kind of like an extended office hour so that if anybody wants to touch base with me on something before they take that final, they can. Otherwise, consider the 2 hours class time that you can use to take the final. So, any questions on any of that? Please do me a favor, please look at the grades in Blackboard. If there's anything that you question, please get back to me. I apologize. I know you guys, but I don't know you all that well because for the most part, you've been so quiet and you've kind of just been little boxes with names in Zoom. I know how important your grade is to each and every one of you, but I'm teaching 5 classes, so I do put in an awful lot of grades. I did an awful lot over the weekend. I might have made a typographical error. Somebody had caught me with one previously. If there's anything in the grade book that you question, please email me and we'll double check everything to be sure. Part of the reason, there's 2 reasons that I like using the Blackboard grade book. One, at any point in time, you can look and see what your average is. And 2, if I make a typographical error, you guys will catch it. So also in the Blackboard grade book, I did submit zeros over the weekend for missing things. I think I told you guys that already. The only part that's not really up to date is your MyLambs average. And the reason for that is I put in your current MyLambs average over the weekend. However, if you're somebody who missed a lot of homework, that average will drop significantly after Sunday the 2nd when I submit zeros for missing assignments. I know there's always this like sticker shock that I get from students after that happens. And part of me wants to do that earlier so you have a better feeling for where you stand. But once I change your grade, you can no longer work on that assignment. And I want to give you the opportunity to play catch up until the end. I know that there are some other people in the math department that reopen all the homework and let people work on it at will at the end of the semester. You can, but that late penalty will still be there because I don't think it's fair to all of the people who worked hard to get things in on time to not have a late penalty attached. So before we get started, any questions on any of this? Are you guys all right if that final becomes optional?
Yeah, that's okay.
Okay. And please make sure you do that problem set final. Some of it was disappointing to me when I was taking grades from MyLambs and putting them in Blackboard. There were several people who never took any of the problem sets. Those are quiz grades. If you didn't do them, they're zeros. Make sure everybody must do the problem set final, whether you're taking the problem set or not, because I just want to have you look at least one assignment, which gives you a retrospective of everything that we've done over the semester to make sure you can retain that cumulative knowledge. So that having been said, next place we usually go is the homework. The homework that's due today is that homework 8.1 on systems of linear equations and 2 variables. I know we have gone over a lot of those already. Does anybody have questions on any of them?
I have a quick question about that final. My meeting disconnected. So the final that's on 5.5, that one is optional.
No, the problem set final is not optional. The final exam is.
Okay.
That's 2, 5, 6. This is a quiz. that everybody must do.
Okay, thank.
This is an exam that will be optional. However, if you do not take it, your lowest test grade does not get dropped. It would be the grade that is dropped. So really the only change again from what's in the syllabus is the final exam only counts once instead of twice, which gives you the option of not taking it if you're satisfied with your test grades, which is why I tried to update that grade book over the weekend so you have a better feeling for where you stand. I'm guessing that most of you won't make that decision until you see how you do on test 4, which the reason that's due on Saturday the 1st is so that I can get it graded before class time Tuesday the 3rd, 4th, so that you know where you stand. Any questions on any of the homework or anything else? If not, this last unit has 2 parts, so systems of equations, which being nobody has questions, I'm hoping that means that you're all masters of the universe with it. And the second part, go ahead.
Actually, sorry, for the 8.1, you know,
Yeah.
I hate doing the word ones. Could we possibly like look at it for a second so I can just like try to like do it on my own and maybe write it
Sure,
out?
but are you all right if we only look at one of them? Because
Yeah,
that
that's fine.
those word problems that we did last week are, many of them are almost identical to these. So pick your favorite, well, I guess I wouldn't say your favorite word problem. It would probably be your least favorite word problem that you don't want to go over. So pick your
Probably,
least favorite word problem and let's look at it.
I'm gonna say probably the last one, 2022.
22?
I
Okay.
got a feeling it's, I looked at before. Yeah, this one. This
Okay,
bad boy.
we did do one like this, but what I'm gonna do, go show after doing all of these blended classes and trying to go over my lab's homework. It wasn't until this past week that I realized probably the best way to do it is to cut and paste the question into the notes so that the work is all done out in the notes instead of just written in on the screen. I'm a slow learner. What can I say?
It's okay.
It's
I am
that
too.
discovery, when you figure out something new with technology. I just wish I would have figured that one out at the beginning of the semester, not the end. Okay, it says, the North Campus of a Performing Arts School, 40% of the students are music majors. At the South Campus, 10% of the students are music majors. The campuses are merged into one East Campus. 22% of the 1,000 students at the East Campus are music majors. How many students did each of the North and South campuses have before the merger? Okay, so what are we looking for? How many students did each of the campuses have? So let's let those be our variables. Let N be the students at North. And let's let S be the students at South. Is that part all right, knowing that we're looking for 2 things? So we'll use 2 variables.
Yeah, that's okay. Thank you.
Now, from those and all of the other words, we have to come up with 2 equations. First equation, we know that when they merge, there's a total of 1,000 students. So doesn't that mean if I take all the students from the North and combine them with all the students from the South, I have 1,000 students?
Yes, that makes sense initially.
Okay. Now, the next thing that we're worried about is music majors. So let's go through and let's write expressions for music majors. At the North, it's 40% of the students. So 40% of the students would be 0.40 times N. We could just write that as 0.4 N. That makes sense.
Yep.
So then for the South, it's 10%. So that's 0.10 S or 0.1 S. And once they merge, it's 22% of the 1,000 students. So that would give me 220 students.
Yep.
Okay, so take this information and change it into your second equation. The music majors at North plus the music majors at South, I'm sorry, my S's look like 5s, is equal to the total number of music majors, 220.
Oh, okay. Cool. Sorry. Thank you so much. It's just
From
it's
there,
hard for
you're
me to,
okay
like-
solving it?
Yeah, I'm okay. As long as like someone or if I can write it out, if someone can help me out, that's amazing help for me because like for me, if I just see a bunch of words, I'm just like, okay, what do I do? But as long as like I have like you or look at past notes, look at the notes and see what I have to do, it's really helpful for me personally.
Okay, now here's the dealio though. I'm going to be that old lady. Realize that if you ever use this stuff in real life is a word problem. So you kind of have to get over like, oh my God, there's so many words in there. What
Yeah.
do I do? I know that at one point in time we offered a foundations class that I really while it was considered a foundations class, some of the material went above and beyond. Some of what was in it was doing things like building exponential functions, which you don't really see until Math 110. But it was a great course. It was put together by a whole bunch of mathematicians and of all things psychologists at Stanford University in California. And the textbook, each lesson read like an article from the newspaper. And you had to go through and read and see what was going on and come up with the math to answer the situation. I thought it was an amazing course, and I wish we would have continued offering it and more folks would have taken it. It was really cool. But anyways, I digress. Anybody else want to look at anything else from this homework?
Thank you, by the way, Mrs. Terrell.
Oh, you're welcome anytime. Hey, that's my job, right?
Yeah.
Okay,
You're good.
you're welcome. Any other questions, folks? If not, let's start looking at angles. I am guessing that if I asked you folks to draw an angle, everybody could. But usually when I ask a class, how would you define an angle? I get met with dead silence. So I'm challenging you guys. Can anybody think of how you might define an angle? We're going to define it as the union. Remember when we looked at sets, we talked about that word union, where we took everything from both things and put it together. So it's the union of two rays. Does everybody remember what a ray is? It's like a half a line. It's 1 point and everything on the side of the line, on one side of that point on the line. So it's the union of two rays with a common endpoint. And so here I have a ray. And then from the same endpoint, I have another ray. And when I put them together, I get an angle. Couple definitions. First, over here, this is the vertex, so that the common endpoint is called the vertex. And these are called the sides of the angle, so that the rays are called the sides. And so we can look at it as a structure, as the union of two rays with a common endpoint. We can also look at an angle in some ways as a motion. And in order to do that, we want to consider an angle that's in standard position. And if it's in standard position, the vertex is at the origin. So we're looking in the coordinate plane. And one side, that's called the initial side, is on the positive x-axis. And so if I draw a coordinate plane, I'm going to have a ray on that positive x-axis, and that's going to be my initial side. And then that other side is considered the terminal side. And the terminal side can be anywhere in the plane. The reason we think of this as a motion, though, is because we're wondering, how did I get there? If I open upward, it's a positive angle. And that idea that opening upward, which is a counterclockwise direction for the positive angles, in my mind, takes that numbering of the quadrants, 1, 2, 3, 4. And it makes sense because I can picture my angle opening upward and going around in that direction. However, instead, if I open downward, or go in a clockwise direction, it's considered a negative angle. And so I'm not just looking at where those terminal sides are, but how did I move to get there? Did I go up? Did I go down? Is it positive or is it negative? So far, so good. Not hearing any concerns, I'm going to turn the page. Is everybody ready?
Yep, I'm ready.
When we talk about angles, we talk about angle measurement. And I think I'm going to go on the assumption, we're going to look at two different ways of measuring angles. First one, I'm going to assume you've heard of before. An angle can be measured in degrees. So I might have something like 1 degree. But what's a degree? How is a degree defined? Well, a degree, if I kind of sort of over here kind of do a hack job and look at an angle in standard position, if I were to go all the way around a complete rotation, that's considered, I think everybody's familiar with the idea that that's 360 degrees. And so we're going to define 1 degree to be 1/360th of a rotation. And so we've got these things degrees. People are more likely to use calculators than not. And so usually people using a calculator, if you've got something smaller than a degree, look at it as a fraction of a degree or a decimal of a degree. But there are smaller units of measurement. What do I mean by smaller units of measurement? If you think about it, if I'm measuring length, I can measure it in a yard and measure how many yards are in something. But there's a smaller unit than a yard, a foot. A foot is like a third of a yard. But then if I want to go smaller, smaller than a foot is an inch, a twelfth of an inch is a twelfth, defined as a twelfth of a foot. But there are smaller units in angles than the degree. And the first one is a minute. And a minute, notation wise, is one with a little prime, a little like apostrophe up in the corner. It almost looks like this slash mark for a foot. And usually when you think of minutes, you think of time, and there's 60 minutes in an hour. Well, it also turns out that there's 60 minutes in a degree. So 1 minute is 1/60th of a degree. And then what's sort of cool is you can go smaller into seconds. And a second has that double prime. And a second, just like with time, is 1/60th of a minute. So we'd say that a minute is 60 seconds, a degree is 60 minutes. If anybody's ever played with degrees, minutes, and seconds, I don't know if that's still a part of the high school curriculum. Last time I taught high school, it was. I think that that function, degree, minutes, and seconds on a calculator is great if you're looking at time, because it would be like, instead of degrees, minutes, and seconds, we can look at it as hours, minutes, and seconds. And so you can divide, time up into those smaller units using that functionality. Not going to really do a lot with the minutes and seconds. Mr. Blitzer in his textbook asks you to find things to the nearest 10th of a degree or 100th of a degree, but I would feel remiss if I didn't at least mention those. When we look at angles, we can classify angles by their measurement. So angles are classified by their measure. And you might see some of these in the homework. First measure we're going to talk about is a zero angle. Oh, hello, before I do that, I want to introduce a new variable to you. This symbol is a Greek letter, theta. And a lot of times, variables for angles are Greek letters. So theta is just a variable that usually represents an angle. And so the first angle measure we're going to talk about is a zero angle. It would be an angle whose measure is 0. And if its measure is 0, it doesn't open at all. And so it would resemble a ray. Next angle we're going to look at is an acute angle. And can I go on the assumption that you folks have heard that phrase, acute angle, before? Can anybody remember what it means for an angle to be acute?
Is that less than 90 degrees?
Beautiful. We're going to say that it's less than 90 degrees, but we're going to add something to that definition. It's got to be bigger than 0 degrees, because going back to where we were before, we don't want every negative angle to be considered acute. So an acute angle is measured between 0 and 90. Then we're going to have a right angle. And can anybody remember the measure of a right angle?
90.
Right angle is 90 degrees, great. And to show something that is a right angle, there's a square in the corner. Do not assume an angle is right unless there are words that tell you that, or unless you see that square in the corner. Because even though it looks right, it could be 89 degrees, it could be 91 degrees, but you'll know that it's right if that square is there or if you're told it's right. Then next we have an obtuse angle. An obtuse angle would be bigger than 90, but less than 180. And so picture again that idea of motion going through 90 degrees, but then further past 90 degrees. And the last one we're going to talk about is a straight angle. And a straight angle is going to be an angle whose measure is exactly 180 degrees. It would be like going through half a rotation. And it actually looks like a line, which is why it's called straight, I guess, because it does resemble a line. Angles by measure, okay.
Yeah, that's fine.
We also classify angles by quadrant. So angles can be classified by the quadrant that their terminal side falls in. So let's draw our coordinate plane. Let's label our quadrants 1, 2, 3, and 4. And again, I'm looking at an angle in standard position. And so does it make sense that if my terminal side is in quadrant 1, it would be somewhere between 0 and 90 degrees? Instead, if my angle is in quadrant 2, then it's open past 90, but it's less than 180. If it goes into quadrant 3, well, I'd be going past 90, past 180, but fall short of 270. So its measure would be between 180 and 270. And then finally, if I'm in that fourth quadrant, I'd have gone almost all the way around, and its measure would be between 270 and 360. But that's if I'm going around in the positive direction. I could also go around in the negative direction. And then if I'm going around in that opposite direction, negative direction, then in the fourth quadrant, it would be between 0 and negative 90. If I'm going around this way, it would be in between negative 180 and, I'm sorry, yeah. Hello, let's try that again. It would be between negative 180 and negative 90. If I'm in the second quadrant, it would be between negative 270 and negative 180. And if I end up in that first quadrant in the other direction, I would be between negative 360 and negative 270. And so we can say what quadrant that terminal side is in. You have to be careful though, because that doesn't allow us to talk about all angles. If we're classifying by quadrant, we're missing what are considered the quadrantal angles. In the quadrantal angles, the terminal side is on the axes. And so if my initial side is that positive x-axis, if the terminal side was on the positive y-axis, that could be 90 degrees. If it's on the negative x-axis, it would be 180. If it's on the negative y-axis, it would be 270. If it's on the positive x-axis, it would be 360. I guess we should also add 0 degrees there. And we could go around also in the opposite direction in negative 90, negative 180, negative 270, negative 360. All of those that are an integer multiple of 90 would be considered your quadrantal angles. So let's go through and let's draw a diagram highlighting those so that this would be 0 degrees, this would be 90 degrees, this would be 180 degrees, this would be 270 degrees, and then here we'd be back to 360 degrees. So far, so good.
Yep.
And we've just been talking in degrees. Am I correct in assuming that things like acute, obtuse, right, straight, and degree measurement is something you've all kind of heard of before?
Yeah, that's good.
The one I'm not so sure about is radian measure. And think of the relationship between degrees and radians, like the relationship between our the standard measurement, where we're measuring things in inches, feet, yards, miles, and the metric system, where it's in meters and kilometers and so on. It's just another unit of measurement. A radian, where a degree was defined as 1/360th of the way around, 1 radian is defined as the measure of a central angle in a circle that intercepts or cuts off an arc whose length equals the radius of the circle. What? Let's look at a picture. Going to try to make a nice circle here. And on that circle, I'm going to find the center and draw a radius. And then I want to picture taking something like a tape measure, measuring that radius and marking that distance off on the circle. Do those look close enough to equal? And then when I do that, this angle here is defined as being 1 radian. And so if I took any circle, no matter how, whoops, that one's an ugly one, no matter how small or how large, and measured that radius along the side, all of those angles would have an equal measure, and they would be defined as 1 radian. So let's say, for example, we have a circle with radius 2. We have an arc length of 4. We want to know what's the central angle in radians. And so I'm going to try to, I should use that circle tool more often. This radius is 2. And then I'm going to have an arc that has a length of 4. Well, if I think of taking that 4, I can cut it into 2 pieces of length 2, and each of these angles would be 1 radian. And so combining them, the sum would be 2 radians. And it gets us to a formula that we can use, where if S is my arc length and R is my radius, I'm going to have theta equal my angle in radians. And the way we took this 4 and divided it up into 2, it's kind of that general idea that the angle in radians will equal the arc length divided by the radius. If you're looking for the angle, this would be the better formula to use. However, if instead you're looking for the arc length, we can think of cross multiplying, and we would get that the arc length is equal to theta times R. So if I look at an example, let's say I have a circle with a radius 4. I have an arc of length 5. I want to find the radian measure of the angle. I'm sorry, I will leave it there. Well, R is 4. The arc is S, that's 5. Theta is S over R, which would be 5 over 4, or 1.25. If we're looking at angles and radian measures, we just write the number with no symbol, or we could write it as 1.25 radians. But if you see an angle equaling a number and there's no degree symbol, it's assumed that that measure is radians, not degrees. Let's look at another example. This time, let's say I have a circle with a radius of 3. I have a radian angle that measures, let's say 1.5. How long is the arc? Well, our radius is 3, our angle is 1.5, and the arc is what we're looking for. I kind of go back to that theta equals S over R as opposed to using that other variation. Theta is 1.5 radians. S is what we're looking for. R is 3. And so if I think of cross multiplying, I get S equals 3 times 1.5, which would be 4.5. This idea of using this formula to find the radian measure of angle in a circle, all right. And it's not like we're going to look at a lot of circles, but we need this idea in order to come up with a way to compare radians to degrees. If you're on this math train all the way through calculus, you'll find that the rules for angles and trig in calculus are based on radian measure, and so you need to become comfortable with it. If this is your final math class, then you can go convert back and forth. But if you're going to go much beyond this, you need to be comfortable working with radian measure. In order to do that, though, we need to be able to convert between degrees and radians. And I guess I could go through and just give you a formula conversion fact that you need to remember. But I think I've told you guys before, if somebody just handed me a formula, it was like Teflon memory. It just slid right off. But if somebody gave me sort of a justification for it, I was much more likely to remember it. So let's go through and let's look at why this is the relationship. And to do that, what we want to do is we want to compare a complete rotation or a full circle. So I'm going to draw my circle in the middle. And as I look at this angle going all the way around, complete rotation, I know that on the degree side, by the way degrees were defined, the full rotation is 360 degrees. Now I want to look and see what happens with that complete rotation on the radian side. On the radian side, I know that my angle is equal to the arc length over the radius. And if I look at a full rotation, if I look at going all the way around that circle, the arc length is the circumference. And so, can anybody remember how to find the circumference of a circle? It's actually pi times the diameter, because I don't know if you folks are aware or not, that's how the number pi is defined. If you were to take every circle in the universe with a tape measure, very accurately measure the distance around the circumference and divide it by the distance across the diameter, it should always equal pi. That's the definition of that number pi. But this talks about diameter and we want radius. Is everybody all right? The diameter is twice the radius. So I get the circumference is 2 pi r. And so if my angle is the arc length divided by the radius, For a full rotation, that's 2 pi r divided by r, which gives me 2 pi. And so all the way around the circle is 2 pi radians. And so if I want to compare them, I'd say that 360 degrees is equal to 2 pi radians. But most people look at that and think, I can make the number smaller. I can simplify it a little bit. Dividing, I'd get that 180 degrees is equal to pi radians. And so if those are equal, I can make a ratio of them. I can make a fraction of them. And since they're equal, the fraction would equal the number 1. And I would use it to just not change what something's equal, but just convert the units. So if I have degrees and I want to change it into radians, I want to cancel out the degrees. So I'll multiply it by pi over 180 degrees. Instead, if I have radians and I want to convert it into degrees, I have to cancel out the radians and add the degree symbol. So I'll multiply by 180 over pi. And so that those are my conversion factors from degrees to radians and radians to degrees. Is this familiar territory for anybody? Let's look at some examples. Let's say I have 90 degrees and I want to change it into radians. I want to do it twice though. Once in terms of pi, and once to the nearest hundredth. Because you're going to find questions that ask you to do both. Sometimes you'll be having a pi in your answer, and sometimes you'll be having decimals. So I've got degrees, and I want it to be radians. I want to think of canceling out the degree symbol. So I'll multiply it by pi over 180. And that idea, I don't know if you folks are familiar with the idea of dimensional analysis, to know which way you write that conversion fact. You want to think of wanting to be able to cross out that unit of measurement. And so this would give me 90 pi over 180, but the fraction 90 over 180 can be reduced. So that would be pi over 2. And so that would be my answer in terms of pi. And a lot of times they'll say, leave it in terms of pi. You're done. That's all you need to do. Instead, if I want to turn that into a decimal to the nearest hundredth, here I'm going to use, I'm not going to use any number that you were taught in elementary school. We're going to use the pi key on the calculator. And so with my calculator, if I take pi over 2, I get 1.57 to the nearest hundredth. So I'm going to stop for a minute and ask you to convert negative 135 degrees into radians in terms of pi and to the nearest hundredth. And also 60 degrees. Give you a minute or two to work on that. I'll be right back. Okay, and so did everybody get up -3 pi over 4? I lost my negative sign. Or negative 2.56. And for the other one, positive pi over 3 or positive 1.05. And again, to reiterate, if it's in degrees, you'll have that little degree symbol. If there is no degree symbol and it's an angle measure, it would be in radians. Any questions?
Nope, this is understandable.
Okay. Is this something you guys have seen before or not so much so?
Not so much so. This is still new, but
Okay. Then we also are expected to go the other way. So let's say I have pi over 5 radians. And I want to express it in degrees. Well, this time we're going to take that pi over 5. And because we want to introduce the degrees, we're going to flip that conversion factor. We're going to multiply it by 180 over pi. If my initial degree measure contains a pi, which it doesn't always do, what helps me to remember is that I'm multiplying it this way, is that I want to think of those pi's crossing out. And so that'll leave me with 180 divided by 5, which would be 36 degrees. Another, if I have negative 11 pi over 6 radians, and I want to change that into degrees. This time, again, we want to introduce the degrees, so we'll put the 180 degrees in the numerator, the pi in the denominator. The pi's would cancel. And that, when I multiply, will give me negative 330 degrees. Where it's a little bit different is if my radian measure does not have pi in it. And so let's say I have 2.4 radians. And I want to change it into degrees. And here you'll probably see a round off word, something like to the nearest 100th. Back in ancient times, you might have been asked instead to do it to the nearest minute or to the nearest second. But instead, we're going to look at those decimals of a degree. And so again, because I have radians and I want degrees, I'm going to multiply it by that 180 degrees over pi. And so I'm going to take 2.4 times 180 and divide it by pi. And this I can't do without my calculator. So let's take 2.4 times 180 and then divide it by pi. And I'm getting 137.51 degrees to the nearest 100th. Is that one all right? Again, remember pi equals that number 3.14, 15, and so on and so on and so on and so on and so on. But an angle of that measure is equivalent to an angle that's 180 degrees. I've seen people get very careless and just start thinking that pi is equal to 180. No, pi is equal to the number 3.1415, blah, 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 blah. But an angle of that measure is equivalent to a 180 degree angle. There are some angles that you're asked to locate in a plane. And you have to be able to do it both in degrees and in radians. So I'm going to draw my axes, my coordinate plane. This is X, this is Y. Sometimes you see these in terms of a circle going around. If you will be taking Math 111, you take a deeper dive into trigonometry than we're doing right now. And that's considered usually a unit circle, a circle with a radius of 1. That's not necessarily the case here. We're just drawing the circle, and we're going to try to label where different angles would be in this circle. We already said our quadrantal angles are our 0, our 90, our 180, our 270, and also our 360. First, I'd like to think of taking this and dividing it into 12 equal pieces like the divisions on a clock. If I divide it into 12 equal pieces, that means that I'm dividing each corner, each quadrant into 3. And so if I were to take that 90 and divide it by 3, that would make this 30 degrees. And so every time I go through that fraction of the circle, I'll be adding another 30 degrees. So I'd count 30. The next one would be 60, then 90, plus another 30 is 120, plus another 30 is 150, plus another 30 is 210, plus another 30 is 240, plus another 30 is 270, plus another 30 is 300, plus another 30 is 330, plus another 30 is 360. And so those would be like the slash marks on a clock for your hours. There is another angle that we're also expected to be able to locate, and that would be if I were to go right through the middle and cut it in half. And so if I go right through the middle, thinking of taking that 90 and divide it by 2, I'll get 45. So whenever I go over that halfway through a quadrant, or I guess an eighth of the way around the circle, I'll be moving 45 degrees. So this is 45 plus 45 is 90, plus 45 is 135, plus 45 is 180, plus 45 is 225, plus 45 is 270, plus 45 is 315, plus 45 is 360. And so you're expected to be able to locate those, but in both directions. We could also go around in the opposite direction. And so, for example, this 330 would also be negative 30, and so on, going backwards. Is everybody comfortable with that in degrees? Because we also have to be able to do the same thing in radians. And so if I draw that same axes and circle, I apologize, the second drawing is a little bit more wiggly wobbly than the first one. Pretend there's straight lines, perpendicular lines in a perfect circle at the center. Well, if I'm in radians, we know that 180 degrees is equal to pi radians. This would be 0 radians. Now, over here, that positive y-axis, well, that's halfway around, so that'll be pi over 2. And so every time I move a quarter of the circle, I'm moving pi over 2 radians. So this would be 1 pi over 2. 2 pi over 2 would take me to pi. This would be, whoops, it would help if I put it in the right place. This would be 3 pi over 2. And then all the way back to the beginning, adding another pi over 2, 4 pi over 2 would take me to 2 pi. Now, if I wanted to look at those slash marks, that would be like the numbers on the clock, where I'm taking that whole circle and dividing it into 12s. 2 pi over 12 would give me pi over 6. And so every time I move like an hour, equivalent of an hour on my clock, that would be pi over 6 radians. So this would be 1/6. Then the next one would be 2/6, but 2/6 reduces to 1/3. 3/6 would be a half. 4/6 would be 2/3 pi. This next one would be 5/6 pi, or 5 pi over 6. 6/6 would take me to 1. Then 7/6, 8/6 would reduce to 4/3. 9/6 would reduce to 3/2. 10/6 would reduce to 5/3. Then we have 11 pi over 6. I have to apologize. That one is always so hard for me to write, because when I write that 11, my hand just wants to give it a hat and turn it into a pi again. Then lastly, 12 pi over 6 would be my 2 pi. In addition, we need to be able to find those middles. Well, if I cut pi over 2 in half, half of a half is a quarter, so this would be pi over 4. And so every time I go halfway through a quadrant, I'm adding a quarter pi. So pi 1/4, 2/4. This middle one would be 3 pi over 4, 4 pi over 4. This middle one would be 5 pi over 4, 6 pi over 4. This middle one would be 7 pi over 4. 8 pi over 4 would take me to 2. And again, if we were to go in the opposite direction, this 11 pi over 6 in the positive direction, in the negative direction would be negative pi over 6, and so on. We'd just be reversing the order. And I think the questions that involve this concept in my labs are for the most part multiple choice. And so there you go. As I look at these angles in a circle, another concept that comes up that's kind of stressed here when I look at did I get there positive or negatively is the idea of coterminal angles. Coterminal angles look the same. They have the same initial side, and they also have the same terminal side. Well, how could that be? Let's go through and let's draw our axes. Let's put our angle in standard position so that the initial side is on the positive x-axis. And let's scooch over here so that we have a second quadrant angle. And I'm not real good at drawing, but let's say that this is a positive 120-degree angle. If all I saw were the sides of the angle and not that arrow in the middle, there's nothing that would tell me that I went in that positive direction. So that angle I could also achieve by going around in the other direction. And that way it would be negative 240 degrees. But I think we could come up with other measures for that angle. If you think of something like in the Olympics when they do the snowboarding or things like that, they talk about somebody doing a 1080 or something like that. And it's somebody who rotates more than once. There's nothing that says I couldn't have got to this by going all the way around 360 degrees and then a little bit further, which would have taken me to 480 degrees. And there's nothing that says that I had to go in that positive direction. I could have started here, spun and said clockwise, negative 360 degrees, and then another negative 200. Oh dear. My stylus just stopped working. Give me a minute. Let me pull the battery out and see if I can coax a little bit more energy out of it. I know I have more of these batteries in the house. I just don't know where. There we go. In another negative 240 degrees, that would have taken me to negative 600 degrees. And if I didn't see the little loop-de-loos telling me what direction I spun or how far I spun, each of those angles would look exactly the same. That's why they're considered coterminal. They have the same terminal side. And if I look at them, we'll see that coterminal angles have measures that differ by 360 degrees. And so a lot of times you're asked to find coterminal angles. We're going to add or subtract 360 degrees. A standard thing that you're asked to find, which again goes back to pre-calculator days when we had to find our trig functions from a table, but it's still an important life skill, is to find it's called the least positive coterminal angle. And that angle will always be between 0 degrees and 360 degrees. I guess technically it could equal 0, but we wouldn't want it to equal 360 because 360 is coterminal with 0. Although 0 isn't positive, so do we want it to be 360 instead of 0? Oh, now I'm muddied the waters, but between 0 and 360. So let's for each find the least positive coterminal angle with each of the following. And first, let's look at something like negative 750 degrees. Because it's negative and I'm looking for something positive, I'll keep on adding 360 until I get positive. So negative 750 plus 360 would give me negative 390. It's still negative, so I'll add another 360, which gives me negative 30. And it's still negative, so I'll add another 360, which will give me 330 degrees. And that's the first positive. So that's the least positive coterminal angle. Instead, if I started with something like 670 degrees, well, that's obviously over 360. So I'll subtract 360. And doing that will give me 310 degrees. There we only needed to subtract once. 310 is less than 360. So that would be the smallest positive. If I were to subtract 360 again, I would get a negative angle. But that's in degrees. In radians, what we'll do is we'll add or subtract. I think we started our discussion of radians with saying that 2 pi radians is equivalent to 360 degrees. So in radian measure, we'll add or subtract 2 pi to get a value between 0 and 2 pi. So for each of these next two, let's find the least positive coterminal angle. If I start with 17 pi over 6, 17 divided by 6 is bigger than 2. So I'm going to have to subtract 2 pi to make it smaller. Again, quick refresher on fractions. Does everybody remember in order to subtract fractions, they have to have a common denominator, which would be 6. So when I subtract 2 pi, I'm actually subtracting 12 pi over 6, which would leave me with 5 pi over 6. And 5/6 is smaller than 2. So this would be my answer. Instead, if I had something like negative 11 pi over 4, it's negative. To get a positive angle, I'm going to add 2 pi. Remember, I need that common denominator. So that'll be 11 pi over 4 plus the common denominator would be 4. 2 is 8/4. So that leaves me with negative 3 pi over 4. Since that's still negative, I'll have to add another 2 or another 8 pi over 4. And so my final answer here would be 5 pi over 4. So far, so good.
Yeah, so far so good.
Then the last thing that you're going to see in this 5.1 homework are a couple of word problems. And so let's look at an example. Let's say we want to find the distance, the tip of the second hand of a clock moves in 40 seconds. If the length of the hand not hand is 4 inches. I'm going to try to picture a clock. I'll have this be my second hand. And in 40 seconds, that's going to move around to someplace like this. We're looking for this arc length. And what we know right now is that the radian measure is equal to the arc length over the radius. But theta has to be in radians. And so the first thing we have to do is find this angle here, theta. Well, in 40 seconds, don't I move 40 over 60 or 2/3 of a rotation? And that rotation is 2 pi radians. And so I'm moving 4 pi over 3 radians. So that's my theta. My radius is the length of the hand, which is 4 inches. And so using that theta equals S over R, I'd get 4 pi over 3 is equal to S over 4. And so when I multiply both sides by 4, I get that S is equal to 16 pi over 3 inches. This would be my exact answer. Instead, if I wanted to round, let's say, to the nearest, let's say, 100th of an inch. I think I lost a letter in that word 100th trying to get it to fit in, but you get the idea. So I'm going to take 16 times pi and divide it by 3. And so that's going to give me 16.56 inches. Again, pay attention. Those usually it's tiny type in blue at the end of a question or beyond the place where you put your answer in my labs. They'll either say in terms of pi or to the nearest. You know, if it's in terms of pi, you're just going to leave that pi symbol in there, but try to reduce whatever fraction you might have if you can. If it says to the nearest, use that pi key on your calculator to change it into a decimal. And that, folks, is the end of what's in that homework 5.1. Everybody all right with that?
Yeah, I'm all good with that.
Then I'm going to just take a little leap of faith and look a little bit at the introduction to section 5.2. And section 5.2 deals with right triangles. And we'll see how far we get with this today. Help. Can anybody remember what it means to have a right triangle?
90 degree.
It contains a 90-degree angle. And so if I have a right triangle, and In this class, we are going to strictly look at right triangle trigonometry. We won't go beyond that. So if any of you have ever done things with like the law of sines and law of cosines, don't worry, we're not going there. Everything that we do, we need to put in terms of right triangles at this stage of the game. As I look at this right triangle, can anybody remember the fancy pants name for that longest side, the side that's across from the right angle?
Hypotenuse.
Beautiful. So the hypotenuse is the longest side of a right triangle. And again, these are only in right triangles. It's opposite the right angle. And then the other two sides that make up the right angle are called legs. And so the legs form the right angle. You're going to find that in some instances, in some problems, Mr. Litzer uses what I refer to as a naming convention. And what it is that triangles are named by their vertices, which are usually uppercase letters. In which case then the sides can be named by their endpoints, but a lot of times the sides are labeled with the lowercase letter from the opposite side, from opposite, a vertex. I'm very sorry, from the opposite vertex. So let's say I have triangle ABC. Could be right, doesn't have to. I've got A, B, C. If it's labeled in that way, the side across from angle A would be referred to as little a. The side across from angle B would be referred to as little b. The side across from angle C would be referred to as little c. Instead, if I have a triangle DEF, this side here, it's opposite angle E, so this will be little e. This side here is opposite angle F, so it'll be little f. This side here is opposite angle D, so it'll be little d. That all right?
Yeah.
Great. And then something else that I'd like to see if you can remember from a past life is what is the sum of the angles of a triangle? Anybody remember what all the angles of any triangle have to add up to?
180 degrees.
Beautiful. The sum of all the angles of a triangle is 180 degrees. So let's look at what happens if I have two right triangles with a pair of congruent acute angles. So here, let me have one big one. Let's say this is triangle A, B, C, right angle at C. Let's have a little one. Let's say this is triangle X, Y, Z, right angle at Z. And let's say we know that angle B is congruent to angle Y. Well, if these three have to add up to 180, and these three have to add up to 180, if those two angles are the same, don't the third angles also have to be congruent? A would have to equal X. And if all three angles are congruent, from one triangle to the other, the triangles are similar. By similar, we mean that they'll have the same shape, but not necessarily the same size. If I could draw and if I measured accurately, triangle ABC would look like it has the same shape as triangle X, Y, Z, but they're different sizes. But what happens is the sides are in proportion. Which means that the ratio of the sides are equal. And that will be true for any right triangle that has a given acute angle. So it's true for every right triangle with a given acute angle. And it turns out that those ratios are pretty important. They're used a lot. And if they're the same for every right triangle with an angle, those values are important. And so they're given names. And those names are our trig functions, the trigonometric functions of a right triangle. So the trigonometric functions of an acute angle. And this is a definition we're going to be using in this class. If you graduate to Math 111, you'll find that we'll be able to give meaning to these ratios beyond acute angles, but we're going to stick with right triangles. So we're only going to stick with the trig functions of acute angles. And so trigonometric function of an acute angle is the ratio of the sides.
Hi, Mr. Rella. I hate to interrupt, but I'm gonna go soon on. Thank you. Did you see my message in the chat? Okay,
Yes, I-
awesome.
Okay, thanks.
Thank you. Bye.
Bye. Is the ratio of the sides in a right triangle containing that angle. And again, any right triangle that would have that acute angle would have that same ratio. So let's say that theta is an acute angle. We define the functions of theta. Oh, wait a minute. There's a word in here that looks vaguely familiar. Does everybody remember what it means to be a function and that idea of function notation? Previously, we looked at algebraic functions, something like f of x, and we needed that like x inside the parentheses to give it meaning. That was what we took the function of. With our trig functions, we're going to need something that's called like the argument of the function, something in parentheses that we're taking the function of. So let's see. I'll try to make this first picture look nice. Whoops, if I can. These toolbars start battling it out between the OneNote toolbars. Oh, actually, there isn't really a right triangle in there. So I guess we'll just wing it. So let's say over here, I have a right triangle. Let's say A, B, C is right angle at C. So then over here, little c would be the hypotenuse. This leg would be opposite angle A, little a. This leg, opposite angle B, would be little b. The first function that we're going to look at is the sine function. Sine, S-I-N-E, of theta. Again, we need something that we're taking the function of. So that'll be my angle, theta. And I have this theory that mathematicians, are intrinsically lazy, don't like to write, and can't spell. So there's an abbreviation for each of these. The abbreviation for sine is SIN. And sine is the ratio of the opposite leg to the hypotenuse. Are you folks all right if I abbreviate a little bit? Is everybody all right? OPP will be opposite.
Yep, that's okay.
So let's look at from each of our acute angles. If I want to find the sine of angle A, for angle A, the opposite leg is little a, and the hypotenuse is C. I could also try to find the sine of angle B. And if angle B is over here, the opposite leg is little b, and the hypotenuse is C. So I know that there are some students that somewhere along the line, I always thought the vertical leg was one and the horizontal was the other. It's not necessarily the case at all. When we're looking for the opposite leg, it really depends on what angle, what acute angle we're going from. Opposite angle A would be little a. Opposite angle B would be little b. And so you always need your angle as a reference before you can set up that fraction. The next one is the cosine of theta. Cosine is abbreviated COS. And cosine is the ratio of the adjacent leg to the hypotenuse. Now that word adjacent, if somebody's adjacent to you, they're next to you. It's the leg that's next to that angle. Realize next to the angle would not be the hypotenuse. We're looking at the leg next to the angle. So if I wanted to find the cosine of angle A, well, this is angle A. The denominator is the hypotenuse, so that'll be C. Next to angle A, adjacent to it, would be little b. And instead, if I wanted to find the cosine of angle B, next to angle B is the leg A. So the cosine of A is B over C. The cosine of B is A over C. And later in the week, beginning of next week, we're going to see an interesting relationship. It's got that prefix co, they have to be related somehow. Do you notice that the sine of A is equal to the cosine of B, and the sine of B is equal to the cosine of A? There's a relationship there that we'll talk about a little bit later. Next one is the tangent function. And tangent is usually abbreviated TAN. And the tangent is the ratio of the legs, but it's always the opposite leg over the adjacent leg. And so if I look for the tangent of angle A, well, from angle A, opposite is little a, adjacent is little b, so that'll be A over B. And instead, if I look for the tangent of angle B, the tangent of angle B, opposite is little b, adjacent is little a, so that'll be B over A. And those are 3 of our 6 trig functions. I don't want to, I'm in the little bit of time that we have left, there isn't really enough time to introduce the next 3. We'll do that next class. I'm thinking next class, rather than starting with a new notebook, I might just add on to this or cut and paste this page. But have you folks heard of sine, cosine, and tangent before?
Yes, I have.
Has anybody learned any little memory aids as to which is which? That sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent.
SOHCAHTOA.
Everybody always says that SOHCAHTOA. And I have to tell you that I don't know if you guys noticed, I'm a horrible speller. And so SOHCAHTOA doesn't do that much for me because I can't figure out how to spell it. But if you're a SOHCAHTOA, it's SOHCAHTOA. I learned it a different way. Back in ancient times, if you put them in order, sine, cosine, tangent, I learned it as a silly sentence. It was something like Oscar had a heap of apples. I've also heard other more questionable versions of that. I think Oscar had a hit of acid, which probably isn't a great one. But there are all sorts of different memory aids to help you remember those ratios. Again, just defining things right now. We'll pick up from here next class. These three basic trig functions, are they something that you've seen before, or is this brand spanking new for some of you?
I've seen these before, and I've done some of them early in, like late in my geometry career when I was in like sophomore year. So it's
Okay,
not new in my memory, but it's not old.
okay, all right. Because it's so funny, I know that the state has changed the high school curriculum so many times. And I think when my kids were in school, I think that they actually started learning these in like 8th grade of middle school. And then it was for a while, it was in the 9th grade curriculum. A lot of time spent on it, a little bit more time in 10th grade and a lot of time in 11th grade. But I know that that has changed so much. So we'll pick up from here next time. And is this enough of a gentle nudge to your memories? Am I going too slow? Am I going too fast? Or is this all right?
This is all good. I got one question. So when you